The presentation that I am going to present is entitled Effect of Phosphorus Doping on Titanium Dioxide as Anode for High-Performance Lithium-Ion Batteries. Rechargeable lithium-ion batteries have attracted attention as one of several promising electrochemical energy storage devices for electronic vehicles, for mobile phones, and also for renewable energies storage due to their high energy density, long cycle life, and zero emission. Graphite, a typical lithium-ion battery anode material, can be cycled at high rates. However, it is unfavorable because of such disadvantages as low power density, low C-rate, and safety concerns. Recent research in the field of electric vehicles has focused on developing new active anode materials with high power density. So titanium dioxide has garnered considerable interest among the new anode materials being for next generation lithium-ion batteries due to advantages such as fast lithium insertion at low voltage and low volume variation during the charge-discharge processes. Titanium dioxide is also an expensive and environmentally friendly material. Generally, titanium dioxide exists in the phases of fragile anatase and brocade. The anatase phase can be considered a host material for electroactive lithium insertion. A crucial disadvantage of anatase structure titanium dioxide is the low electric conductivity owing to its wide bandgap energy, a significant hindrance in lithium-ion battery anode material, resulting in dramatic performance decreases at high rates in the charge-discharge process. A doping technique is considered an efficient means of increasing the internal surface electrical conductivity. Doping with cationic or anionic dopants contributes to the formation of more open channel and active seats for lithium-ion transport via expanding interplanar spacing of titanium dioxide lattices. In this work, we are interested on phosphorus doping using phosphoric acid as phosphorus precursor. So concerning the experimental part, the P-doped titanium dioxide nanoparticles were synthesized via sol-gel method. Typically, titanium tetra-isopropoxide was used as titanium precursor, then sodium alginate biopolymer as complexing agent were used in the form of solution, and phosphoric acid was used as phosphorus precursor. The crystal structure of the doped and non-doped titanium dioxide were identified by XRD, as shown in this figure. These diffraction peaks, which are attributed to the diffraction planes of anatase titanium dioxide, indicating that the crystal phase of titanium dioxide remained after phosphorization treatment. The structure properties of the two materials were further examined by Raman spectroscopy. So these obtained bands represent the Raman active modes of anatase phase of titanium dioxide, which are coincide and confirm the XRD results. For the absorbance measurements and compared to pure anatase, it is observed that the phosphorus doping extends the wavelength response range into the visible light region. The band gap of titanium dioxide and P-doped titanium dioxide was 2.9 and 2.8 electron volt respectively. This result confirms the effect of phosphorus doping to reduce the band gap and improve the conductivity of titanium dioxide. Concerning the electrochemical measurements, so the discharge charge curves are illustrated in this figure for the doped and non-doped titanium dioxide. So as it can be seen here for both materials, the first discharge curves has to plateau at 1.9 and 1.7 volt, representing cathodic and anodic peaks of anatase titanium dioxide nanoparticles respectively. Moreover, there is less polarization and less capacity loss, reversible capacity loss for the P-doped electrodes. This result could be attributed to the improved electronic conductivity. Our cyclic voltammetry technique shows the presence of two cathodic and anodic peaks at 1.7 and 1.9 volt respectively, which can be attributed to the insertion extraction of lithium ions in the TiO2 anatase nanoparticles. So these cathodic anodic peaks confirm the results obtained with the galvanostatic discharge charge profiles. This figure presents the Coulombic efficiency together with the cycle capacity profile for 50 cycles. So an excellent Coulombic efficiency of about 100% is demonstrated for both doped and non-doped titanium dioxide electrodes. Moreover, the capacity retention of the non-doped electrode after 50 cycles is only 86% and 89% for P-doped titanium dioxide. So these excellent electrochemical properties would be explained by the smaller particle size prepared by biopolymerization method that permits more rapidly lithium disinsertion process. So as a conclusion, the titanium oxide doped with phosphorus was synthesized by the Soldier method. Titanium oxide in the anode phase has been synthesized successfully as confirmed by the various structural analysis techniques. The P-doped titanium dioxide material present high electrochemical performances in comparison with the non-doped titanium dioxide. And thank you for your attention.